Hey there. So this lesson is going to be more abstract, okay? We're not going to do a lot of examples. On the contrary, we're not going to do any examples. We're going to write some theorems. Not hard theorems, but theorems always require proofs, and proofs take a kind of a little switch in your mind to thinking abstractly, and sometimes it's a bit challenging. So these are the two properties that we defined. The property of a set of vectors being linearly dependent and the property of a set of vectors being linearly independent. And we already have a feeling for these notions because we did many, many examples. Now I want to write some theorems. So here's the first theorem. So theorem number 1. Any set that includes, this pen is deceased, any set that includes, beautiful, the zero vector is linearly dependent. That's a theorem. Okay? If you have a set of vectors v1, v2, up to vk, and one of them is the zero vector, it's automatically linearly dependent. Let's prove this. Proof. So here's the set. Our set is of the form v1, v2. Somewhere here there's the zero vector, right? And then there are a bunch of others, up to vk. The zero vector can be vk, it could be v1, I don't know. But this is a set of vectors that contains the zero vector. Do you agree? In general, that's what it looks like. This is a set which includes 0. Do you agree? Now, in order for this set to be a set of linearly dependent vectors, I have to show you a linear combination of these vectors, not all of which coefficients are 0, that gives 0. Here you go. Take 0 times v1 plus 0 times v2 plus 0 times all the other guys. But when you get to 0, take 1 times 0. That's not a 10. It's 1 times the 0 vector. Let's emphasize this. Okay, the 0 vector. Plus, all the vectors in your linear combination are going to have 0 coefficients. But this vector is going to have a coefficient 1. Do you agree, first of all, that this gives you the 0 vector? Right? And this is I'm missing the word is. This is a linear combination where not all alpha i's are 0, right? Because here's an alpha that's not 0, which gives 0. That's the definition of being a linearly dependent set. Do you agree? Everybody? Okay, so any set that includes the 0 vector is automatically linearly dependent, by definition. Okay, theorem number 2. Two vectors, suppose your set only includes 2 elements, 2 vectors. So 2 vectors are linearly dependent if and only if one is a scalar multiple of the other. Okay, so 2 vectors are linearly dependent. Reduces to a simpler statement. 1 has to be alpha times 2. V1 has to be alpha times V2 or vice versa. Okay, let's prove this. All of these theorems are not just vague, abstract nonsense. They're very, very, very useful. In fact, the previous one we already used in our justification of method 2. Remember when we said that if there's a 0 row, it's a linearly dependent set? Remember that? Okay, all of these we're going to use a lot, all over the place. Okay, they're very, very useful little observations. None of these are very deep theorems. There are some very deep theorems in algebra. These are not. Okay, these are very, very basic and very useful. Okay, so so we need to prove two things here, two directions. These are two statements in one. Okay, so let's start by proving this direction. So suppose we have two vectors that are linearly independent. We have to show that one is a scalar multiple of the other. So what does it mean that they're linearly dependent? It means that we can write alpha 1 v1 plus alpha 2 v2 equals 0, where not both alpha 1 and alpha 2 are 0 simultaneously. Okay? Where either alpha 1 is not 0 or alpha 2 is not 0, or both. Right? Do you agree that that's what it means to be linearly dependent? Okay? So if alpha 1, so this implies, if let's say alpha 1 is not 0, then we can divide by it. So we can move this to the other side and divide by alpha 1. So we can get that v1 equals minus alpha 2 over alpha 1 v2. If alpha 1 is not 0. Do you agree? And there you have it. v1 is a scalar multiple of v2. So this is if alpha 1 is not 0. And if alpha 2 is not 0, we can write v2 equals minus alpha 1 over alpha 2 v1. So there's an or here. So in this case, v2 is expressed as a scalar multiple of v1. Good? So this proves one direction. So this is not good. Let's write the word so here. So this is the proof of this direction. If they're linearly dependent, then one is a scalar multiple of the other. Good? The other direction, now I'm proving this direction. Assume that one is a scalar multiple of the other. Assume that one is a scalar multiple of the other, and show that they're linearly dependent. So what does it mean that one is a scalar multiple of the other? If v1 equals alpha v2, that's what it means for one to be a scalar multiple of the other, right? Then, so if v1 is alpha v2, then, well, v1 minus alpha v2 is 0. And that's it. This is a linear combination where not all the coefficients are 0, because this is a 1, which gives 0. And by definition, if you have such a linear combination that gives you 0, where not all the coefficients are 0, the vectors are linearly dependent. Good? And of course, if v2 is alpha v1, it would work just the same. Good? Clear? Still very, very basic, very close to the definitions, but very useful facts. Good? Everybody good on theorem number 2? Okay, theorem number 3. Where is it? There it is. Any set that contains a linearly dependent set is also linearly dependent. So you take a set of vectors, v1 to vn, and suppose some of them are already linearly dependent, then the entire set is linearly dependent. Let's prove that. You should feel by now, after doing examples and starting to get a more precise feelings for these definitions, you should feel, yep, that sounds true. That sounds true. If they're linearly dependent, what you should think is that means that there's somebody extra already, and you throw in a few more guys, you make the set bigger, of course they're still going to be linearly dependent, right?
Just put 0 in front of the ones.
That's already the proof. That's correct, but that's already the proof. I'm giving you the intuition. I'm saying why intuitively this should be true. Okay, good? Okay, so let's write the proof. So let V1 through Vk be linearly dependent. So we're taking a set of linearly dependent vectors. And now let's add some vectors. So it's going to be a set that contains a linearly dependent set. Consider the set V1 to Vk. And now let's add some. Vk plus 1, Vk plus 2, all the way up to Vn. I threw in n minus k more vectors. So this is a set that contains a linearly dependent set. I want to prove that this is linearly dependent. Okay? So why is it linearly dependent? Because we know that there exist alpha 1 through alpha k, not all 0, such that alpha 1 v1 plus alpha k vk equals 0. We know this holds because this set is linearly dependent. Do you agree? That's the definition, right? Therefore, if we look at alpha 1 v1, for these exact same alphas, alpha 1 v1 plus alpha k vk plus, and as you said, add zeros, 0 vk plus 1 plus 0 vn, this is still going to be 0, right? Because this was 0, and we knew that because the original set of v1 to vk was linearly dependent. I added nothing. I just added 0 times all the other guys. It's still going to be 0. Do you agree? But there you have it. You have a linear combination of all the guys in the bigger set, which gives 0, where not all the coefficients are 0 because not all these alpha i's are 0. Do you see that? Okay, so we have a linear combination that gives 0, and this implies that v1, vk, all the way to vn is linearly dependent. Good? Once again, very basic, very useful. Okay, so when you take a set that's already linearly dependent, throw in more guys, you can't help it. They're still going to be linearly dependent. Maybe by removing a few you could make it independent. That's going to be hidden in some of the next theorems. We're only at number 3. But by adding more, you can't make a dependent set independent. Good, everybody? Okay, number 4. So there's an obvious price to taking a new fresh marker, which is that it's harder to erase. But you don't care, you're just sitting there, right? I'm the one.
Is it a theorem or?
During the... It's an empirical theorem. Okay, so number 4. Number 4. A set contained in a linearly independent set is also linearly independent. So this is in a sense a complement to theorem number 3. Okay? If you start with a linearly independent set and you take a subset of that, of course they're going to be linearly independent. Okay? And let's write the proof, but it's really looking at 3 in the proof is going to be plain logic, doing plain logical arguments on 3. Okay, so let's call the set U. So let U1 be a linearly independent set. And let U2 be a subset of U1. Okay? I'm taking only some of the elements in U1. If U2 were linearly dependent, then by theorem number 3, U1, which is a set that contains it, would also be linearly dependent. But U1 is linearly independent. So that's obviously can't happen, right? Clear? So if U2 is linearly dependent, then so is U1 by theorem 3. This is a contradiction. We started with a linearly independent set. By theorem 3, if you take a subset that was linearly dependent, it would also be linearly dependent. In contradiction, to start. So therefore, U2 has to be linearly independent as well. Okay, I probably have my tenses wrong here, right? It's not if U2 is linearly dependent, then so is U1. I probably should say something like, had U2 been linearly dependent, then U1 would also have been, or something like that, right? But hey, we can do some non-formal English here. Okay, as long as we're formal on the math, that's important. Is this clear? Is the idea clear? Okay, so this is really not a new theorem. It's just a restatement of that theorem. But I wanted to nevertheless write it in its own right because, again, very useful, very useful. Clear? Everybody good? Okay. Number 5. And again, you can feel number 4 intuitively. If you have a set where nobody's extra, you need everybody, and you throw some guys out, you're only left with the partial set, of course you're still going to need everybody, right? Nobody's going to suddenly become extra, because if it were extra, it would have been extra in the bigger set as well. Okay? Good? Okay, number 5. A set, let's do this. Let's write number 5 and number 6 together because their proofs are going to be related. And let's have some common notation above them. So let S be the set V1, V2, all the way up to Vk. So this is a set of vectors. And let's assume that not all Vi's are 0. Okay? If all the Vi's are 0, then obviously it's a dependent set and there's not much to say about it. It's boring. Do you agree? Okay, so assume we have a set of vectors where they're not all zeros. Okay, and in particular, we could assume that V1 is not 0. Okay, assume V1 is not 0. Okay, let's stick the one vector that we are assuming that's definitely not 0, let's call it V1. Okay, And then there are two theorems. So number 5 is going to be S, this set of vectors, is linearly dependent if and only if one of the VI's is a linear combination of the others. This should already feel very intuitive to you. We know that being linearly dependent means that we can, then one is extra, at least one is extra. We can write one as a linear combination of the others. Okay, but that's not the definition, right? The definition was slightly different, so this requires proof. Okay, and 6 is going to be S is linearly dependent if and only if one of the VI's is a linear combination not just of the others, but of its predecessors, of the ones that came before it. So if it's V4, then we can write V4 as a linear combination of V1 to V3. Okay? A linear combination of its predecessors. It's a double S, right? Looks double S-ish to me. Is this right?
Yeah. So.
Yeah? Good. You're spelling it on. Good. Good. Well, then you can pick up any spelling mistakes that I have. So is this the correct it's? Or should there be a... that you can do, right? Because it's a correct word and...
It's context related.
It's context related. Okay. And what's the answer? Does anybody know English well enough?
Correct.
It's correct. Okay, I always get confused on this one. I'm asking whether there's the little thingy here. Okay, let's prove these two. Okay, and you might ask again, why is number 6 necessary? Why do we care that it's a linear combination of the guys in front of it? Because it's useful. Okay, in proofs and in arguments. Okay, let's prove 5 and 6. So we have to prove, in fact, 4 things, because 5 is an if and only if statement, therefore there are 2 directions to prove there, and 6 is an if and only if statement, so there are 2 directions to prove there. Okay? But in fact...
6 is like the last one and 5. We need only one.
Right, some of these directions follow from the others as special cases. So let's see what follows. So here are the proofs of 5 and 6. So let's first prove this direction of 5. So 5, this direction. This direction is the direction saying that if one of the vectors is a linear combination of the others, then the set is linearly dependent. Okay, so let's do that. If, let's say VI, one of the vectors, is a linear combination of the others, alpha 1 V1 plus ... alpha I minus 1 VI minus 1 plus alpha I plus 1 VI plus 1 plus alpha K VK. This is a completely general linear combination of the others, right? I skipped VI because VI is a linear combination of the others. Do you agree? So if VI is a linear combination of the others, then if I move VI here, I'm going to get a linear combination of all of them that gives 0, where not all the coefficients are 0, because VI's coefficient is 1. Do you agree? Then 0 equals alpha 1 V1 plus ... plus 1 VI plus ... plus alpha k v k.
Should be 1 minus 1.
Minus 1, you're right, because I knew. You're right. Minus 1 vi plus alpha k vk, right? And this is a linear combination where not all the alpha i's are 0 of all the vectors that give 0, which implies, therefore, what did we call the set? S is linearly dependent. Do you agree? Good? Okay. Do you agree that this direction of 6 follows from this for free, right? Because what did 6 say? Let's look at this board again. So we proved that if we know this, then the set is linearly dependent. Here we wrote not just any linear combination, but a more restricted linear combination. But it's still going to imply, by the same exact reason, if one of the VI's is a linear combination of its predecessors, then obviously it's a linear combination of the others, right? And therefore, the set is linearly dependent. Do you agree? So this direction of 6 follows from this direction of 5. Okay, good, everybody? So let's write that. This direction of 6 follows from this. Do you agree? Everybody good? Okay, now let's do the other direction. So let's do this direction of 6. Okay, I want to show that if the set is linearly dependent, then one of the VI's is a linear combination of its predecessors. Okay, so this is the only slightly non-basic idea that's hidden in everything we did so far in this lesson. Okay, so what do we know? We know that the set is linearly dependent, right? That's in this direction. The data, what we know is that we're looking at a linearly dependent set, right? So S is linearly dependent. Therefore, we know that there exist alpha i's, giving us a linear combination which is 0, where not all the alpha i's are 0. So there exists an alpha 1 v1 plus alpha 2 v2 plus ... alpha k vk that equals 0, where not all alphas are 0. This is what it means for S to be a linearly dependent set. Okay? All we know is that not all the alphas are 0. Some of them could be 0, right? So let's take the biggest one that's not 0. Okay? So let J be the greatest index such that alpha j in this linear combination is not 0. So maybe there are 15,000 vectors here, but only the first 3 are not 0. All the rest are zeros. So j would be 3. Okay? Good? Okay. So let j be the greatest index such that alpha j is not 0. Then we can write alpha 1 v1 plus alpha 2 v2 plus ... alpha j vj equals 0. Do you agree? Because all the rest have 0 coefficients, so leaving them there or removing them doesn't make any difference. Do you agree? Okay. And now, we know that alpha j is not 0. We can move this to this side and divide by minus alpha j, just like we did in the case for 2 vectors. Okay? And therefore, so Vj can be written as minus alpha 1 over alpha j minus alpha 2 over, minus alpha 1 over alpha j v1 minus alpha 2 over alpha j v2 minus minus alpha j minus 1 over alpha j vj minus 1. Good?
That's it.
That's it. We wrote Vj as a linear combination of its predecessors, of only vectors with lesser indices. Good?
I didn't get the part where you got the let J be the greatest index that we can write. I didn't get why the...
So first of all, by the fact that S is linearly dependent, we have such a combination. Okay? Not all the alphas here are 0, but maybe alpha k is 0. All we know is that there's at least one that's not, but maybe some of them are. Okay? So I want to remove all the ones that are. Okay? Because if they are, if we would, suppose we would try to do this trick and say Vk is a linear combination of its predecessors, which are all the rest. It would mean move this to the other side and divide by alpha k. But maybe alpha k is 0. You can't divide by it. Right? So therefore I'm saying, okay, Vk is not going to do it. It's not a linear combination of its predecessors. Throw it out. Throw all the guys out until you reach from the right, one that has a non-zero coefficient. Okay? And why is this equal to 0? Because all the alphas with index bigger than j were 0. Because alpha j was the non-zero one with the greatest index. So do you agree that this fact is true? Okay? And now, since I know that alpha j is not 0, I can move this to the right-hand side and divide by it, add a minus, and I get this. Okay, good? Okay, so what remains is to prove this direction of 5. Okay, so let's look. So do you agree that we just proved this direction of 6? In fact, we completed the proof of 6.
And 5 follows from.
Right, exactly. So once we know that if a set is linearly dependent, one of the VI's is a linear combination of its predecessors, well, in particular, it's a linear combination of the others. Take all the rest of the coefficients to be 0. So this direction of 5 follows from this direction of 6. Okay, so number 5, direction left to right, follows from this. Good? Okay, so this completes the proof of 5 and 6. Whenever you do such things as prove two theorems simultaneously, you have to be very careful not to do any cyclic arguments. Okay, not to do things of the form, prove 6, use it to prove 5, and then use 5 to prove the other direction of 6, or all sorts of things like that. You have to be careful not to do cyclic arguments. But here we didn't. We proved this from scratch, then we proved this from that, then we proved this from scratch, and then we proved this for that. We never proved something based on something else and then proved something else based on that. Okay, this was completely kosher. Okay, good? Okay. That's 5 and 6. I want to quote one more theorem. It's kind of not real. It doesn't really belong to this specific lesson, but it is a theorem about linear independence. So I might as well add it here. The reason is that it's not a general statement about vectors. It's related again specifically to matrices. Okay, specifically. So here's theorem number 7. A homogeneous system of equations AX equals 0, that's a homogeneous system, has a non-trivial solution if and only if the columns of A, are linearly dependent. Okay, so this is another situation where there's nothing deep going on. It's just the method, translating things. We just need to translate this correctly, and the proof will just be right there in front of our eyes. Okay, so remember, recall that in general, a system AX equals B can be written in a different way as, so in particular AX equals 0 can be written as, and this we discussed previously, as x1 A1, where A1 is the first column of A, plus x2 A2, where A2 is the second column of A, plus xn an equals B in general, or 0 for a homogeneous system. Okay, where these are the columns of A. Remember this? We discussed it previously. Everybody remember? Okay. So what's the statement here? The homogeneous system has a non-trivial solution. Well, if and only if there's a non-trivial solution to this. But what's a non-trivial solution to this? A non-trivial solution to this means this is nothing but a linear combination of the columns of A, right? Where not all the coefficients are 0, because we're assuming there's a non-trivial solution, that gives 0. Do you see that? So that's it. There's nothing more to say. Having a non-trivial solution to the system means having xi's not all 0. Xi's are the components of x, right? Means having xi's not all 0 that satisfy this. But this is precisely saying that A1 through AN are linearly dependent. So AX equals 0 has a non-trivial solution if and only if A1 through AN, which are precisely the columns of A, are linearly dependent. Do you agree? So this is a very characteristic example of a situation where the theorem may look like there's something big to prove, and some theorems may look very naive, but in fact require some non-trivial and sophisticated technology to prove. But this is not the case. This is just rephrasing it in a way where it's just obvious. It's just the restatement of the same fact. Okay, good? Okay, so we're going to stop here. We're almost done with this broader topic of dependence and independence, and we're almost means we have a few more things to say, and then we're going to continue to discussing the dimension, the concept of the dimension of a vector space, and the concept of what is a basis for a vector space. And those things are going to be related, for example, to the phenomenon that we noticed that 2x2 matrices are essentially the same vector space as R4, which are essentially the same vector space as polynomials of degree 3 over R. Okay? Okay, so that's it for today.